Last time on CCNA 1, Chapter 7, we talked about the IP4 addressing binary conversion, so on and so forth. Now, we've arrived at IPv6. IPv6, the need for it, how it coexists with IPv4, how their unicast, multicast, and, well, what they use instead of broadcast works on IPv6 network. So let's get into it. Maybe if I can. There we go. All right. IPv4 issues is running out, or so they tell us. Is it really? Yeah. Only, what? Afronix should still be surviving? Well, I mean, we're still hanging on to that IPv4 for dear life. We'll see. We'll see if they ever force us really to go to IPv6. They keep on saying that we'll have to, but we'll see. But anyway, yeah, IPv4 is running out. So IPv6 solves that problem. We talked about that in previous video, I believe, that there are 4 point something billion IPv4 addresses, and there's 340 undecillion IPv6. Okay, so as we integrate IPv6 with IPv4, we need ways to have them coexist on the same network or over networks. Okay, so one way we can make that happen is something called dual stack, which basically allows your devices to run both IPv4 and IPv6 simultaneously. That's pretty much it. They'll support both addresses, so no matter which one it receives, it'll go ahead and either route it or receive it and de-encapsulate it. So that's what IPv4 v6 dual stack is. So know the term dual stack. Tunneling is a way for an IPv6 traffic to travel over an IPv4 only network. Okay, so basically what's going to happen here is your IPv6 packet is going to be encapsulated inside of an IPv4 packet. It's kind of just a package to let it be transmitted over this IPv4 only network. For all that network knows, it is an IPv4 packet. Well, because it is, with an IPv6 packet hiding inside of it. So that's what tunneling is. You're basically packaging your IPv6 packet inside of an IPv4 packet to get it through an IPv4 only network. So that's our other technique. The last technique that we have is translation, which we haven't talked about network address translation, or NAT, just yet in terms of just normal NAT. But basically here you're translating an IPv6 packet to an IPv4, or the other way around through this network address translation, or NAT64 process. So we usually use NAT for private versus public IP addresses with an IPv4 address. You can also use it here for IPv6 to IPv4 and vice versa. So know those three terms: the NAT64, or translation, tunneling, and your dual stack. The IPv6 structure. All right, we're going to get into some hexadecimal and hextets. So here we are. We talked about binary to decimal translation. So we need to talk about hex to binary. Really, that's what you're going to be converting to and from. You're not going to be too concerned about decimal here. Just hex to binary. So here's how it's going to work. Let me see how I want to lay this out on the Excel spreadsheet. Before I do that, you got hextets, which are 4 hexadecimal digits. So 4 digits here that could range from 000 to FFFF. Okay, that block of 4 is a hextet. Now it's not 8 digits, it's just saying that it could range between there to there. All right. So that's 16 binary digits. How? Because each hex digit is 4 bits. So you got 1, 2, 3, 4. You got 4 blocks of them. So 4 times 4 is 16. 16 binary digits. Okay. And we're going to take a look at how to translate that here in a second. We've seen this chart before in a previous video, so I'm not going to go through this again. But we've got some IPv6 addresses. And so how do we translate one of these addresses to binary if we needed to, or one of these hex tets? That's all I'm going to do. I'll do one hex tet worth of information. It's the same concept we use from binary to decimal, so hopefully that translates here for you as well. So let's take a look at it. All right. So I'm going to go ahead and bring up Excel again. So here's Excel. There's the chart we used. So what I'm going to do is take a hextet and convert it to binary. Okay. So I've got this hextet, for instance. What's a interesting one? How about 0db8? 0db8. I'll translate that into binary so you can see how that would work. So we got over here, I'll type in 0db8. Alright, so each one of these values, 0 is 4 bits, D is 4 bits, B is 4 bits, 8 is also 4 bits. Okay, we're just going to go ahead and really we can break them down one at a time. So I'll take the 0. Okay, well that's going to be easy. I've got that 0. It's going to just be 4 zeros. 1, 2, 3, 4. Alright, easy enough. I've got the D here. I'm going to right align that actually so it's a little easier to see. We got our D. The D, if we remember, hexadecimal goes 0 through 15. Only when you get, let me go ahead and I'll jump back here. When you get to 10, you go to A, and then 11B, 12C, 13D, 14E, blah, 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 15E. So this D is going to be 13. So A is 10, B is 11, C is 12, D is 13. All right. So we need to get 13 out of our chart up here. I'm sorry, these numbers should not be here right now. Okay, just that's our chart. That's our plain chart. All right, so we need to get 13. We only use the first four here in hex. So let me go ahead and I'm just gonna give these guys a black, red background because we are not using those in this situation. Oh, doesn't want to take. Let's try that again. There we go. So only using these guys when you're calculating a hex value, hex binary value. There are only 4 digits. Okay, so 13. How do I get this binary value for this hex digit? Okay, or hexadecimal value. Well, I got 13. Can I subtract 8 from 13? Yes, I can. Same thing we did for binary to decimal. So can I subtract 8 from 13? Yes, I get a 1. I'm left with 5. Right? I have a 5. Can I subtract 4 from 5? Yes, I get a 1. Okay. I've got 1 left. Can I subtract 2 from 1? No, I can't, so I get a 0. Can I subtract 1 from 1? Yes, I can, so I get a 1. Okay, so this is 1, 1, 0, 1. Okay, this should be 4 zeros over here. It's not letting me display that. Let me just put 0.0000. That is not going to work either. Okay, it's 4 zeros. Don't mind that decimal there, the decimal place. That shouldn't be there. So I just wanted to get 4 zeros into that cell. All right, so our 0 is 4 zeros. Our D is 1101. Again, we're ignoring this little decimal place. All right. Your B is going to be 11. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10. B is 11. So we got our B. It's going to be 11. 11 minus, let me wipe this out. 11 minus 8, yes, you can do that. So we get a 1. That leaves us with 3. Okay, 3 minus 4 does not work. We get a 0. 3 minus 2 does work. We get a 1. That leaves us with 1 left. 1 minus 1 does work. We get another 1. Okay, so you can see kind of how we're going here. So I've got 1, 0, 1, 1 for my B. Okay, and then the 8. 8's going to be easy. 8, I'll go ahead and wipe this out. And, well, we've got an 8 here. 1, Okay, everything else is 0 because, well, 8 minus 8 is 0. And so we have 1, 0, 0, 0 for your 8. So typically you're not translating the whole dang IPv6 address to binary, thankfully. You may need to do a portion of it, but you don't need to do the whole thing. So that's how you're going to do it, though. Same type of concept as our decimal to binary. It's just you need to keep in mind that as you get to 10, you go to A, 11B, 12C, 13D, 14E, 15F. It's not that bad. We'll get some practice with that in class. Okay, so there's your conversion. All right, you will need to know that a bit. I believe you will get 1 or 2 test questions on that. All right, so we'll move along, moving right along. These IPv6 addresses are very long, so there are ways to shorten them. Okay, so there's a shortened technique and a preferred. They call it a preferred technique, but you don't need to use it. You typically write out the shortened technique because, well, it's easier. Okay, so our rules when we are going to write out a IPv6 address. We've got to omit leading zeros. So if you have a hextet that starts with a few zeros, you're not even going to write them out. Okay, you're just going to start, well, wherever your first number starts, or if it's all zeros, you just leave a 0 there. Okay, so this is it. This is the IPv6 address written out completely. Down here you have the IPv6 address with those zeros eliminated. Okay, so you could write it 2001, eliminate the 0 here, DB8, eliminate the first 3 zeros, you get a 0, eliminate those zeros, you get 0, 0, 0, eliminate the 0 before the 200, and there you go. So those are leading zeros in each hextet. That is on a per hextet basis. Okay, so that's what you get here, eliminating the leading zeros. Hopefully, as we discuss that in class, it'll become more clear. We'll move along. Eliminate all 0 segments. I don't know why that says all. Interesting. Well, it says all, and then it says only one may be used, which is the rule. You can only eliminate one string of zeros in your IPv6 address. So what does that mean? If you have a long string of zeros, for instance, this address here, okay? What have they? Okay, there we go. They have it down here. I was wondering where it was. We have this string of 3 hextets worth of 0. What you can do is wherever you have your longest string of hextets that are all zeros, you can eliminate those by just doing a double colon to represent that string of all zeros. So in this case, you got 3 hextets here that are all zeros. This double colon down here represents those zeros. Okay? You can only do that once. You can only have one double colon entry to eliminate your longest string of zeros. Okay? So you couldn't just do a double colon here, for instance, on this string of zeros, because, well, if you had 2 double colons, you wouldn't know where the extra zeros went, essentially. Are there 2 here and 2 there? Are there 3 here and 1 here? You wouldn't know, basically. But if you only have one double colon entry, you'll know where all those zeros lie. Okay, so you can only do this once. You can only do this once. Better example is down here. Okay, I've got 2 hextets of 0 in this preferred address on that side. I've also got 2 over here. Okay, so compressing this, the way they've written it out here, they've got a double colon here, okay, which represents these 2 sets of zeros. And then the second set, you actually have to have the 0 in there and the other 0 in there. So you know where the zeros belong. Okay. Now, like it says here, you can only use the double colon once. But that doesn't mean that you had to double colon the first set of zeros. Okay, if you have the exact same amount, 2 hextets and 2 hextets, it wouldn't matter. Usually you do your longest one, and there is no longer one here. They're equal in length, the length of the zeros. Okay, so you could have a double colon here, or if you wanted to, you could have placed the double colon over here and had these 2 zeros over on this side instead. It doesn't matter. You write it out how you feel like you want to write it out. In fact, it says, or, I'm sorry, I missed that. Down here it shows you could put it in either place. It wouldn't matter. Okay, it's just your preference. You can only use it once though. Okay, you couldn't put the double colon here and the double colon there. You can only use it in one place or the other. So we'll talk about that more in class as well. Alright, if you have a whole string of zeros, you could basically eliminate all but this compressed version of the address. If you got a whole bunch of zeros, just double colon to 1, and that's enough. Okay, whether you're writing it out in a table or an IP address on your host device, or writing a command on your router, that would be enough. Okay, all 0 could be just double colon compressed. Okay, so those are your rules for writing out IPv6 addresses. You've got the double colon, you've got limiting all leading zeros, which we saw up there, or omitting all leading zeros. So those are the 2 items that you've got. Then we'll get into types of IPv6 addresses. So the next section is going to be types of IPv6 addresses, and the types that we have are as follows. You've got Unicast, which we had Unicast for IPv4. It's essentially the same thing. There are some different types of Unicast addresses that we'll talk about in just a second. You've got Multicast, again, same type of thing, one to many. Anycast is not the equivalent of a broadcast. Okay, Anycasts we won't talk about too much. Basically, a packet is sent to an Anycast address. It's routed to the nearest device having that address, but it's not something we talk about in CCNA 1 really. So we'll focus on Unicast and Multicast. You'll see in the note that IPv6 does not have broadcast addresses, but through Multicast it has a process, a process that is similar to broadcast, which is called an all nodes multicast. So basically you're sending a packet to all nodes on your network, which would be just like a broadcast. So though it's not called a broadcast, you have a similar process that will perform the same task as a broadcast. So your IPv6 does not have labels like host portion, network portion of the address, but there is an equivalent, which is your prefix length, which would be like your network portion of your address essentially, and then your interface ID, which is pretty similar to the host portion of your IPv4 addresses. So you can kind of think of it that way. You don't have a subnet mask, but in the prefix you do have something called a subnet ID that we'll talk about a couple slides from now. So the length of your prefix ID, kind of similar to your network bits in an IPv4 address, can be expressed in this slash some number, either 0 to 128. Typically, you can see here it's a slash 64. That basically tells you the equivalent of your network bits for IPv6. It's your prefix length would be a slash 64. So just like in our CIDR notation with IPv4, we had a slash and some number. IPv6 uses a similar technique here for its prefix length. So it can be a slash 0 through 128. You can see how it breaks down here, prefix and interface ID, each having 64 bits. Of course, adding up to 128 bits, and that's what our IPv6 addresses are. They're 128 bits. So you've got that. So on this slide we have our IPv6 unicast addresses, different types that exist in IPv6. You got global link local, loopback, unspecified, unique local, embedded. Your global unicast address is very similar to your public IP address in IPv4. In IPv4, your public IP addresses are all unique. So is your global unicast. It is unique. The only difference is each one of your devices in your home network or your small office network is going to have the ability to have a global unicast address. You don't need private addressing it anymore in IPv6 because we have enough IPv6 addresses to go around. There's no need for private addresses. So your global unicast address is a unique address configured for your device, either statically or dynamically. Your link local address is a address that you have to communicate within your local link or within your own subnet or network locally. It's going to be separate from your global unicast address, and they typically start with FE80, and it is separate. It's a separate entry that you use, or a separate address that you use to communicate within your own network or subnet. In IPv6, they call that a local link. Okay. Just like in IPv4, we have the loopback address, which is used to test your TCP/IP protocol stack. You've got your unspecified address. You've got a unique local address, which is, well, kind of different, not something we've seen in IPv4. They are categorized as a unique local address that's used for local addressing within a site or between a limited number of sites, maybe within a company's network. And they typically start with FC00 and FDFF. Then you could have a IPv6 with an embedded IPv4 address in it, which is what you see at the very bottom. Let me correct myself on the unique local. I said there really wasn't an equivalent in IPv4. There actually is an equivalent in IPv4. It's called RFC 1918 private addresses that are similar to your unique local address in IPv6. So that's, again, in IPv4 it would be called RFC 1918. So we'll go ahead and move forward talking about link local unicast addresses. So again, link local is for just your local network or your subnet local link, as it would be called in IPv6. So it's kind of different. If we're used to IPv4, which most of us are, it's kind of like an extra entry. You would think that, well, why do we need this when we have MAC addresses? It's just an extra address that IPv6 is tacked on here. So you need to have one. If you have a IPv6 configured, either you are going to assign a link local address yourself, or it's going to be assigned for you. Any device with IPv6 enabled is going to have this link local address. And again, it is used to communicate within the same network or subnet. You can see all the addresses start with FE80, and that's typical. Your link local addresses are going to start with the FE80. They're actually an FE80/10 in the FE80/10 address range. So here we have some uses of the IPv6 link local address. It can be used to send routing information between routers, and most of the time it'll be used as the default gateway for a device running IPv6. Rather than the global unicast address, you would use the link local address instead. And we'll move on from there. Alright, so we're going to talk about these unicast addresses in IPv6. So the only global unicast addresses that are being assigned right now are the ones that start with 0010 through 0011, which translated is going to be a 2000 through 3FFF. So all of the IPv6 addresses that are being assigned, the global unicast addresses, are either going to start with a 2 or a 3, which basically equals out to about an eighth of the IPv6 addresses that are available. Okay, so right now we're only using 1/8 of IPv6 as a potential. You can see the 3 different sections: the global routing prefix, the subnet ID, and the interface ID. Those to the global routing prefix and the subnet ID are going to go together. So they're both contained in this /64 that we see for the prefix. Okay, so again, the global routing prefix is pretty similar to the network portion of an address, and your subnet ID still does have to do with the subnets in your network. The subnet ID is used by an organization to identify the subnets within its site, and the larger the subnet ID, the more subnets will be available. And again, the interface ID is like the host portion of your IPv6 address. It's called the interface ID because a single host may have multiple interfaces, each one having one or more IPv6 addresses. So you get this interface ID over here, which is 64 bits typically. That's what they recommend, is that you use a /64 and have 64 bits for your interface ID most of the time. And I guess there it is again. That's what I just stated on the previous slide. Subnet ID is used by an organization to identify subnets within a site. Interface ID, equivalent to the host portion of the IPv4 address, used because a single host may have multiple interfaces, each having one or more IPv6 addresses. So there you go. We'll move on. So reading our IPv6 global unicast address, you can see you've got the first 4 hextets total make up the prefix. But remember, the prefix is made up of both the global routing prefix and the subnet ID. So you'll see that both of those are contained there. The first 3 hextets, global routing prefix, as you see there. The next hextet is your subnet ID. Then the last 64 bits, or last 4 hextets, are your interface ID. Okay, and that's in a /64 situation. All right. Or I should say a /64 prefix. And configuring an IPv6 global unicast address is on this slide. So it's not very different from when we configured our IPv4 addresses. If you look at it, it's just instead of typing IP address, then typing in the address you want, no shutdown, you just add v6, and that's pretty common. If you want to use the same commands you use for normal IPv4, you just add a v6 for it, and it tends to be the exact same command when you're configuring IPv6. So if you know your IP commands for IPv4, you should know your IPv6 commands pretty well, because all you have to do is add a v6 to it. So that's configuring IPv6 on a router. On a host, you've got, well, not too different from IPv4. You're just going to type in what you need, your subnet prefix length, your default gateway, which could be a link local address, or it could be your global unicast. Here they're using the global unicast. So nothing too mind-blowing there. So here we are with a dynamic configuration for IPv6. So this is going to be different. It's different from, well, anything we see in IPv4. You've got stateless address auto configuration. Okay, that's SLAC, stateless address auto configuration. You're going to need to know SLAC versus SLAC and DHCP versus DHCP v6 only. Okay, this is where you're going to get your IP address. This is where you're going to get, or your prefix length, your default gateway information, your DNS addresses. All right, so you need to know these 3 options. You can see option 1, SLAC only. Everything you need is going to be learned from the router that's configured with SLAC. You're going to get your prefix length, your default gateway. You don't need to communicate with the DHCP server at all. Okay, so that's SLAC only. And again, that's stateless address auto configuration. You've got SLAC and DHCP v6, which means you'll get some information from your router. Then you'll get some information from the DHCP server. So the router will give you your information, but you need to get other information such as DNS addresses from a DHCP server. So basically for option 2, you're going to use SLAC to create your own IPv6 Global Unicast address with the router's help. The router's link local address is going to be set up as your default gateway, but you'll need to use that DHCP v6 server to obtain other information such as the DNS server addresses and a domain name. And then there's option 3 where the router doesn't have anything for you. It says get everything from the DHCP server. I cannot help you. So in this situation, you are using a stateful DHCP server to obtain a global unicast address, DNS server addresses, domain name, and all other information. Alright, so that's stateful. Remember, Slack is stateless. This last option is stateful. So here we have an example of option 1 in action. You are soliciting information from your router. I need addressing information. The router advertises, okay, here's your prefix, here's your prefix length, here's your default gateway information, giving you all that information for option 1. Option 2, you got a device, again, it's going to ask for information. The router is going to say, here's your goal, here's your prefix length, default gateway, but you will need to get DNS information from the DHCP v6 server. So you need to get that information. You'll communicate with the v6 server. That will give you your DNS information. Okay, so there will be a little 3-step process. You'll need to communicate with both the router and the DHCP v6 server. And we don't have a graphic for option 3. You're just going to get all the information from the DHCP v6 server, so that's stated down here at the bottom of the slide as we move forward. So on this slide, after you get your prefix and prefix length either from your router through Slack or from the DHCP server, you are going to need some interface ID over here. So the way that is generated can be one of 2 ways. You've got a EUI64 process and randomly generated, and we'll talk about both of those in the following slides. At least I think we will. Yes, we will. Alright, so this is an interesting process, the extended unique identifier 64 process. This is what we see here. This is based on your MAC address. So you're going to say your MAC address is this address up here. Alright, so stay with me now. We're going to break this MAC address down into binary bits. Okay. When you break it into binary bits, alright, first of all in the middle you're going to insert FFFE. That's what you see down here. You break up the OUI and the device identifier bits or portions of the address. You insert FFFE, which translates to these bits you see here. Okay. The other part is you need to take the 7th bit that shows up in this first hexadecimal value and you flip it. So where it started out being 11111100, that 7th bit, that second to last 0 here, okay, we're going to flip that 7th bit from a 0 to a 1, and where this started out as FC, now it is FE. So we've got FE 99, 99 is the same, 47, 47 is the same. We put FFFE in the middle every time, then 75, 75, CE, CE. Everything else matches up. Alright, so again, this process is it's going to take the 7th bit, flip it, and just add FFFE to your MAC address. That's how you get your EUI64 interface ID. Okay, so if EUI64 is in use, you can probably tell because you'll have that FFFE in the middle there. Okay, and we'll move forward. Alright, or it can be randomly generated. As random as computers can be random. So that started with Vista, so most likely you're going to see a randomly generated interface ID there. Okay, so here we are with a EUI generated and a randomly generated. Again, you can probably tell pretty quick which is which, because if you just look for that FFFE in the middle there, you can see that, well, this is EUI 64, and there's no FFFE in the middle here. So you can see that that's randomly generated. Okay. Link local addresses with a randomly generated versus EUI. Still, you got FFFE in the middle. All right. Again, this is dynamic. You wouldn't be making these yourself. And then you've got just a random number. So that FFFE is really what is the tell if EUI is being used. All right. There you have again another example. This is from a router. If you did show IPv6 interface brief, again, you take your IP commands, add a v6 for it. That's how you get your v6 commands. All right. Here is the command to set up your link local addresses. Okay, we saw how to set up a global unicast address in one of our previous slides. This is how you set up a link local address. Basically, it's IPv6 address. You type in your link local address and then link local after it. Okay, so that's all you're going to need to do there. It's very similar to the other process we use for global unicast. It's just you got link local at the end, and you want to make sure it's in most likely the FE80 range. So you've got your show IP interface brief, you've got your link local address, you've got your global unicast address. If IPv6 is enabled, then you will have on an interface that is, you will have some sort of link local address, whether you configure it or not. It's just an automatic thing that happens. So you can configure it yourself, or if you don't, you just enable IPv6 on an interface, you are going to end up with a link local address, whether you like it or not. So it's just something that happens automatically. Here's an example of what your IPv6 routing table would look like. IPv6 ping. Don't be too afraid of IPv6. IPv6 multicast. This video is getting really long again. It's going to be 2 half-hour segments. All right. So, I mean, not this one, just both together will be 2 half-hour segments. Assigned to IPv6 multicast addresses. So for IPv6 multicast, we have 2 types, assigned multitask and solicited node. Your assigned multitask is going to be for pre-assigned groups. 2 common groups are the all nodes multicast, which is the same as a broadcast, as you can see here. That's going to be the FF02::1 destination address. You've also got an all IPv6 routers multicast, so that's going to be a FF02::2. So that's sent to all IPv6 enabled routers. And, well, in case you didn't know, the way to enable IPv6 on a router is IPv6 unicast routing. That will turn on IPv6 on your router. Solicited node multicast is similar to the all nodes multicast address. The advantage of a solicited node multicast address is that it is mapped to a special Ethernet multicast address. This allows the Ethernet NIC to filter the frame by examining the destination MAC without sending it to the through the IPv6 process to see if the device is the intended target of the IPv6 address. So you can see here we've got the Ethernet NIC determined, not for him, not for that guy, but yeah, this one's going to accept it. So that's a solicited node multicast address. And I think we're so close to being done. So close. Connection verification. Okay, using ICMP to test network connectivity using ping and traceroute. Okay. So we've used ping quite a few times to test connectivity. Let's see an example of it here. Move, move, move. Let's move. There we go. So the ICMP messages can be used by both ICMPv4 Our common DNS, ICMPv4 and ICMPv6, include host confirmation to see if a host is there on the other line. We've done that quite a bit. Destination or service unreachable. Whoops, sorry about that. So the destination or service unreachable would be when a host or gateway receives a packet it can't deliver. It can use the ICMP destination unreachable message to notify the source that the destination is unreachable. Okay. Time exceeded is just your time to live reaches 0. Okay, and it's going to say time exceeded. We talked about time to live or hop count in IPv6. And it can also be used to communicate if there was a route redirection. All right, so there we go. Non-reliable protocol provides for messages to be sent. Yep. Okay, moving along. So IMCPv6 has a couple features that IPv4 does not. One of them being router solicitation and router advertisement messages that are communicated through IPv6. We talked about Slack and how the computer will, or your host device will request information from your router. So that's a router solicitation message that you'll send out. The router advertisement would be the response saying, no, I have your information, or I don't, letting it know whether it needs to use option 1, 2, or 3 for Slack. So those are done through IMCPv6, and you'll see that here. Okay. When a host is configured to, still talking about Slack and the router advertisement and the router solicitation. So we've talked about Slack before. Just know that that's an IPv6 process. What else? Still, neighbor solicitation. So if you know the IPv6 address of a device in your network, you can use this neighbor solicitation to find out the MAC address of a device that has an IP address you know about. It's similar to an ARP request in IPv4. So you have these NS or neighbor solicitation messages, and the neighbor advertisement message would be the response sending back that MAC address. Okay, so that's another feature of IPv6. You've got neighbor solicitation to find out the MAC address of an IPv6 address you have in your routing table, so you can have the MAC address of that device. Okay. What else? Still the same thing, I think. Yep, asking for the MAC address again. That's similar to ARP. And again, that's neighbor solicitation, neighbor advertisement, exchanging MAC address information, much like an ARP request. And this is duplicate address detection. So you can use that same process, that neighbor solicitation, to make sure your IPv6 address is unique. You want to use an IPv6 address. You're going to ask all of your neighbors on the network, if anyone has that IPv6 address, send me your MAC address. If you don't get any response back, then you know that your address is unique. That's duplicate address detection. Okay, pinging. We talked about pinging 127.0.0.1 to test your TCP/IP protocol stack a little while back. So that's just that process in action. Test local connectivity. You're pinging some device on your local network. We've done that. Again, we're just testing connectivity with an echo request, echo reply, pinging some device on a network. Nothing really new there. Traceroute, testing the path it takes to get from one device to another. That's what a traceroute does, or a traceroute command from your host device. It'll bring up the path that is taken. And believe it or not, right before we hit the 30-minute mark, we are done. So this is the second part of Chapter 7. You have a first part that you can take a look at as well. And we'll be discussing the commands to set up your routers based on IPv6 in class. So it'll be a lot of IPv6 on routers that we do in Packet Tracer in class to practice these concepts, as well as some binary, hex, and whatnot conversion. So that's it.